So today we are going to handle feedback control. This feedback control will be generally shown like this. You have a reference signal, or it's sometimes called set point. So this is what is our desired output. Reference output or set point is something that we want as output from our control system. Then we have our system. I am putting it somewhere else. This is actuator input. Then you have your system. There is sensor output. Then this sensor output, you can feed it back through again. I will say two methods of doing it. So there is a controller. Then this controller output goes and it's compared with this reference. So this is plus, this is minus, and it goes to actuator and the system. This one, as we know from our block diagram knowledge, this is feedback loop. So that is one way of doing it. There is another way of doing that same thing. Here is again reference. Or set point. The comparator, plus minus. This is error. This error goes to the controller. Then controller acts on actuator. And this actuator then provides the input to the system. System has sensor outputs. And this goes back straight to this. So what we have in the first configuration, whatever actuator input goes to the system, then output comes out of the sensors. Whatever is the sense signal, let's say YT, this YT state goes to the controller, and then it is compared with the reference, and that is going to the system. Whereas in the second one, you have reference applied, then sensor output, it is compared with the reference, the error goes to the controller, then controller applies the whatever gives power to the actuator, and this actuator then controls the system. So these two configurations are possible. Both are feedback loops. This is feedback loop. This configuration here is called controller in the feedback loop or feedback path. And this one is called controller in the forward path. Other one is called controller in the forward path. Both of these configurations are possible. Now, most often you will require some kind of computer. If you are going to do a numerical control, some kind of computer or some kind of electronic circuit in this interface. So I will show you how to do a computer integrated control. So one thing that is most important before all these is that the controller and feedback path
Yes, sir.
must be active, not passive. What does it mean? That means that a reverse signal should not be fed back through the control. For example, let's say I have some kind of spring mass damper system, very simple system. Let's say I am measuring somewhere here, let's say velocity. I am, let's say, integrating it. So I get position. Then this position, I am comparing with a reference position. Reference position or set point. Then whatever error comes, I multiply with a gain, some gain, let's say alpha, and then I apply a force here. Let's say this is a, this we give, okay, this is a actuator, piezo force actuator. Of course, it is connected somewhere to the inner shell frame, otherwise it cannot provide force. So what happens? We want this mass to deflect by a certain position. We are measuring the velocity of that mass. Then we are integrating that. And then we are comparing what is the current position with respect to the reference position. If there is an error, we are multiplying that error with some constant, and that whatever value comes, that much amount of force we apply. So if let's say this set point is x dz, if x is equal to x dz, error is equal to 0 and applied force is equal to 0. Good. Okay. That's so far so good. No problem. But what is more important is that this part of the circuit, the control part of the circuit, it should not do a reverse actuation on the system. What does that mean? That means, okay, let's model this part as a one graph. Let's say we have velocity sensor, some one junction I, C, R. Then here, from here, we are having a flow activated bond. I am not putting the sensor as it is. I am completing the entire loop. Okay. So we have a flow activated this thing, let's say, and we have, this is our thing. Then we have some kind of integrator, let's say. Then this is a flow activated bond. We have some reference position. This I apply by some kind of reference signal. Let's say x dz. This is plus, this is minus. Then I put a gain. So what are we having? Okay, this gain, these signals, let's treat them as flow. Although this is position, let's treat them as flow. So this gain is a gyrator. This is a gyrator, that is alpha. So this side is flow. Then we get a force, effort, which we apply here. All right? Okay. Now if you look at it, okay, we causal this, let's say this. Here E is there, F is present. What must be effort here? Effort must be 0 here. Effort must be 0 here. Effort must be 0 here. Effort is, by default, it is 0 here. So only place power exists is in the actuator. Which one? This one. This is my actuator part. Rest of the circuit should be powerless. So how it can be powerless? Power obviously comes from outside.
So
what? Yes.
So should we need? So how is the flow coming? So there were positions, right? So from that
Yes,
summation point,
for modeling purpose, I have assumed that signal is a current. It has become, ultimately it has got converted to an electrical signal. Is it not? After sensor, it has got converted to some kind of electrical signal. Okay. So that electrical signal I am assuming to be a flow. This XD position, how do you give position? You are, let's say, having a microcontroller. How do you give position? That's no more a position. You give a set voltage or you give a set current. All right. So in that controller domain, you flow and effort are actually means even if it is displacement, or whatever variable, it is either a flow or an effort.
So then the integrator will be a transformer.
You can, integrator is not a transformer. Integrator is a op-amp integrator. If you want to model it analog wise, it will be an op-amp integrator. If possible, I will show you. You might remember your basic electronics course. Okay, you can put a op-amp with this forgotten one buffer resistance will be there. Okay, then you have a capacitor here in the output side. I will do that. I will find out. Okay, it's this thing. So whatever it is, okay, the important thing is that this is a power bond. This power should not come here. Power should not flow opposite direction.
Sir, there is a doubt, another doubt. Like in
Yes,
the gyrator, we have put effort.
Oh, I muted you. Please unmute yourself. I muted all because of
Hello?
feedback. Yes.
Yes, sir. So in the gyrator, we have put an effort is equal to 0.
Yes.
But that can't be, right?
Because
there is effort.
Yes, that can't be. Okay, that can be.
No.
So that's
wait. If there's effort and flow on the left hand side, then there must be effort and non-zero effort and flow on the right hand side as well, right? Of a gyrator.
Yes. That's why I am putting activation. Okay, I will show you what that means. Okay, I am going to show exactly that, how to make it. All right. Okay. If I do not do that, then what will happen? This actuator will start giving. Let's say I am applying a force here. This will generate a velocity. That velocity will come back in reverse direction, and through sensor it will apply a force maybe on the mass. Okay, maybe it will affect some other parts of the controller. So what we need to do is we need some kind of isolation. So control circuit, it requires isolation. What is that isolation? Isolation is an op-amp. This is buffer op-amp. Even if you do not amplify the signal, you might require that buffer. So you have some signal, let's say, you have something, let's say some current I am giving. Here you will have both, okay, both voltage and current, okay, which are generated from tank circuit. This is external power. But on this, because of high input impedance, sorry, this is voltage, VIO. So here, because of high input impedance, current will be almost equal to 0, right? Okay. So, okay, you can do it reverse also, right? Okay. So what is required is, okay, you must isolate your controller part from the system. System's response itself should not go back and affect the dynamics of the controller. That is what is important. All right. So it should be only a signal connection, whereas in practice it is actually wires. There are actually wires. We don't connect signals by signals. How do you connect a controller to a system? You will put some kind of wiring. Now that wire, through that wire, if you apply certain voltage, some current will come back. So that to isolate that, you have to use these buffer operational amplifiers. So though we will not show them in the circuit, it will be assumed that those buffers are present at appropriate places. All right? Okay. Those buffers are needed to prevent the system from affecting the controller. Sometimes it may happen that if that buffer is not there, you will get such a high voltage or such a high current that your controller circuit will burn. Usually, if you are using a card, a data acquisition card or any kind of, let's say, Arduino or any other chip, you will find that input impedance is already built in with the card. So it's already built in. Wherever you have input and output ports, it will automatically isolate. So in a computer, so computer control, we will assume buffer is included in ADDA card. Okay, analog to digital or digital to analog, it's same card. Okay, same card. We call it ADDA card. So it's there, already included. Buffer is there. So what we have, some computer, this thing, you have reference. What do we give that reference? We give that reference to the computer. So that is reference or set point. This is basically data. You give data to the computer. Some kind of data we give. What else we give? How this computer is interfaced? This computer is interfaced through a card. So it has a card. So you have from there, you have here, okay, a power amplifier. This is low power, very low power. Computer gives very low power output. You need a power amplifier. So you have some power amplifier, maybe one, maybe many. It might be a box. Sometimes you will find power amplifier is a big box with lot of op-amps. So power amplifier, then you have actuator. We usually do not show all these in the diagram, but they are there. Then you have, power amplifier, actuator, okay. Then you here I have missed something. So that's what I have missed something here. Okay. So this will give to D by A card. D digital to analog. Then it goes to power amplifier. That's an analog signal. Okay. Then we have actuator. Then we have system, which is also an analog system. Then this is goes to sensor. So here I am explicitly showing the sensor. Usually we model whole thing inside that system. Now this sensor, this goes to analog to digital, AD. So analog to digital goes here. Inside this, of course, you have all plus, minus, whatever, and controller. Controller is a program. So you give data. Controller is a program in the computer. Computer outputs something that is a signal. That signal is converted from digital to analog domain. Then that analog signal is amplified. That's applied to an actuator. Then actuator acts on the system. System signal is sensed by sensor. This sensor signal is a digital analog signal. That analog signal is converted to digital, and that goes to the computer. So that is how the whole control loop is done. You have a power amplifier here, and we have, of course, within this ADDA, D by A and A by D plus buffers is a single card. It's one card. That is buffer heading. This is one card. One card. You might take the computer inside. Instead of computer, you might have a let's say some kind of microcontroller. So all those D by A and AD and buffer and computer / microcontroller can be a single card. So everything can be a single card. All right. So what actually inside happens is you have a conversion from analog to digital. You have a conversion from digital to analog. There are buffers to protect your circuit. Buffers to prevent reverse flow. And there is, of course, some kind of processing power involved, either from a computer or a microcontroller. So obviously you will need all these kind of things if you have a complex control. If you have very simple control, you don't need a microcontroller or any computer. So we will go back to those simpler cases. That is controller in the forward and controller in the feedback loop. What? Controller in the feedback path. I make a small table. I am drawing the simplest thing without putting all those buffers and all those things out, because those are anyway there. So this is plus, minus, error. Let's call it E. Then controller in the forward path, you have controller here whose transfer function is HS, then system whose transfer function is given as GS. This is YS. And here you have plus, minus, this goes to system, GS, output is YS, then here we have HS. Okay, GS is plant or system transfer function. HS is controller transfer function. So some plant is there, some controller is there. All right. Now, this GS is the plant or system transfer function. We call it open loop transfer function. I will tell you again. Afterwards, we will come back to open loop transfer function. Okay. So open loop transfer function means, okay, it is the transfer function that is ratio of YS. GS is ratio of YS to this one. Let's say U bar S. Whereas now US is here. If you take this as some input here to the GS and YS is output of GS, then the ratio of YS divided by this U bar S is GS. All right. So that is what is called open loop transfer function that we derive. Whereas for this entire circuit, the US now is the reference signal. So US here is reference. So US is reference, input Laplace transform. All right. It's not same as the input that was used to calculate the transfer function. Now we want to find YS by US for the closed loop system. That means with feedback. Right? We want to find out the transfer function for the closed loop system. What happens when we have established this feedback loop? So let me call this one as U bar S. U bar S. So here GS is equal to YS by U bar S is open loop transfer function. G, let's say I put subscript, GCS is equal to YS by US is closed loop transfer function. All right, is that clear? For my plant input and I find output, the ratio of Laplace transform of output to Laplace transform of input is plant's transfer function. But now, because of this, putting a controller, then finding error and so on, my system has got changed. Now to this control system, the input signal, it is different. Maybe my spring mass damper system, I had force as input, but after implementing the control system, the input to my closed loop system is the desired displacement. So my input has changed. Outputs have not changed. Remember, output has not changed, input has got changed. So that with that changed input, I need to find what is the transfer function of the entire system, including the controller. That is what is called closed loop transfer function. Finding it is pretty easy. We can write that U bar S. Let's say I derive it for this case. This is A, this is B. For B, what we have here, it is Ys. Here what is the value? Ys times Hs. So you can write U bar S is equal to Us, that is my new input, minus Ys Hs. This we can write. Further, what we can write? We can write that Ys is equal to U bar S times Gs. So we will put it here. So this is Us Gs minus Ys Gs Hs. So this we will simplify. What we get? Us Gs is equal to 1 plus Gs Hs. I have taken this Ys other side and brought this Ys this side and Gs that side times Ys. So is that correct? Is it correct, students? Okay. So then for this we can write Ys by Us, that is the closed loop transfer function, is equal to Gs by 1 plus Gs Hs. So this is my feedback formula, which you have to remember. This is loop gain rule that you have to remember, that if you have a transfer function Gs in the forward path and a feedback transfer function is Hs, then the net resultant feedback system's transfer function is Gs by 1 plus Gs Hs. And remember that at this point, at the comparator, there is a plus sign and minus sign. If both become plus, then you can convert one of them to minus by taking a minus in the Hs. So you can write here minus Hs and here it is plus. In that case, if this is plus, you can put a minus here and here also minus Hs. So in that case, that will turn out to be Gs by 1 minus Gs Hs. Alright. So for a negative feedback loop, with a negative sign at the comparator, you have the relation Gs by 1 plus Gs Hs, that is the closed loop transfer function. So this is for...
Sir?
Yes.
Shouldn't it be minus?
No.
1 minus?
How? Where is it
Sir,
minus?
because we are multiplying GS both side and then we are taking difference, right? So it's if we take out YS common from the right hand side, you get a
take from
minus.
here. Take from here. Bring this part towards left. Bring this to left. So you have 1 plus GSHS into YS. Okay, with that minus sign becomes plus. So this is for the controller in the feedback loop. This is one rule for controller HS in feedback loop. The other one is pretty easy. If you have derived this, you can also write that straightforward. What we have for controller in forward loop? A, we have this plus minus here HS, then here GS, this. This is what we have. This I will rewrite as, instead of deriving that relation, I am straight writing plus minus. I have here some G star S, let's say. And here I have some H star S. Where G star S is equal to, I multiply those two, GSHS, and H star S is nothing, it's 1. So these and these are same. Then my transfer function becomes G closed loop S is equal to YS by US is equal to G star S by same formula, 1 plus G star S H star S, and I substitute there, I get GSHS by 1 plus GSHS. So this is another formula. The difference is both formulas denominator is same. In one of them GSHS appears at the top. In other one only GS appears at the top numerator. That is the only difference. Otherwise they are the similar formula. Then there are very subtle parts, okay, which I am going to tell you. So we have, let's say, configuration like this. And configuration like this. So this has become equivalent to straight GSHS by 1 plus GSHS, and this one has equivalent to this one is like this, GS by 1 plus GSHS. Now, if you remember your block diagram rules, you find that, say, this YS, this is YS. YS is equal to YS refers to velocity. All right, and this is, let's say, a force. This is some force. So this is velocity, this is some force. Then what is HS? Can be a resistance, R, can be R is to R, can be C is to K. It's possible. Okay, it can represent some kind of, here is some velocity. Some velocity comes, some x dot s. Then you might have R times here, R times x dot s, or K times integral x dot t dt, that is x dot t dt, that is, we can write K by s, x dot s. All these are possible. So here in left side diagram, you can connect it to several block diagrams you have drawn previously. Whereas you didn't encounter anything like right hand side in your block diagram drawing. Did you find anything like this on the right hand side? This kind of thing? This kind of thing was not seen. So we will say this is a causal control loop. This needs active elements for implementation. Whereas the left side model, this can be replaced by physical system components. This is a causal model. Causal control loop. So the differentiation is very clear. Let's say you are measuring from somewhere velocity, and after doing some kind of control action, you are applying some kind of a force. You can say whatever that controller model is there, maybe I can build it by an analog circuit. I can put some capacitors, resistances, and so on, and I can make an analog circuit to exactly represent that same control action. So I do it outside the system. I take the measurement, do all that analog circuit, I pass it through the analog circuit. Maybe I have a real mechanical damper, or instead of that, that I represent that by a electrical resistance. Instead of a mechanical spring, I represent that by a electrical capacitance. And I ultimately produce some kind of a force, equivalent of a force, which I then apply on the plant. That's possible. Whereas in the other one, you are taking something which is not the measurement. This is not the measurement. This is already the error. This is already error. This is the measurement. Why yes? Here it is error. So this is an error, and let's assume this measurement is x dot s. that is S times Xs. Okay, S times Xs. Okay, X Laplace transform of x dot t, that is S Xs. Okay. So this is a velocity, and let's say this is a force. So this error has no physical meaning. We have taken a difference between a force and a velocity, or force and a displacement, something we might have taken. This error no more has any physical meaning, so that controller also will not have any physical meaning. All right? So left side model, it is called a causal control loop. Right side model, it is called an acausal control loop. But in both of them, interestingly, the denominator is same. That is what is important to note, that the denominator of both the forms is same. So is there any confusion? Get it clear. Otherwise, things will go on becoming more and more murky afterwards. Any confusion, students?
Sir,
Yes.
sir, input is a reference value. So how it's force?
Which one? Input.
Input in.
Input can be anything. Input can be anything. What you want from the system. Okay. Let's say I want some force in that spring. I want that the force in the spring should be 100 Newton. That's input. Okay. I want velocity of something to be something. I can have displacement. Input can be anything. Alright? So that is my requirement. That input is my requirement, what I want. Right? Okay. The measurement may not be of the same quantity. I may not be measuring force. I want my force to be something, but I am measuring something else. That's also possible. All right?
Okay, sir.
Okay. So I will take an example and demonstrate all these. Okay. So
Excuse me, sir.
don't worry. Yes, yes.
Sir, what have
Well-
you written in on the right hand side? What have you written? Laplace of Xs is equals to what have you written there?
I have written Laplace transform of x dot t is xx. There is nothing like x dot s. Okay. Like this one, x dot s. What's that x dot s? It is Laplace transform of x dot t. Okay. That is s times xs. All right. So what we want to learn here, what is more important to learn here is let Gs be Ns by ds. This is open loop transfer function. Let's put any closed loop for anyone. One case it is GCS. Acha. Let's also say let HS is K. That is constant. You don't write here K by S. Alright? Okay. When you have a constant gain, it's not Laplace transform of the gain. Right? If you have a constant gain, let's say input is something, let's say it is some input, okay, U, right? Then you have a gain K, Y, then HS is K. You don't say I will take Laplace transform of K and make it K by S. Okay, that's Y by YS by US. Okay, this is US YS. Right? That is same as YT by UT. If it is only a constant. So if you have a constant feedback gain, that is called a proportional control, you have GS by 1 plus GSHS is equal to NS by DS divided by 1 plus k times ns by ds, which when we simplify, ds will go out, will be ns by k times ns plus ds. So that is my closed loop transfer function for k gain in feedback loop. Whereas GCS is equal to GS HS by 1 plus GS HS is equal to k times ns by ds by 1 plus k times ns by ds is equal to kns by kns plus ds for k gain in forward loop, forward path. It's loop, not loop. So what is there? Denominator is same. Same whether k or hs is in forward or feedback path. So stability of the closed loop system for both the cases is same. You don't have to separately handle stability of putting a controller in the feedback path or putting a controller in the forward path. They are all the same. You analyze one of them, the same results are applicable for the other one. As far as stability is constant, because stability only is determined by the denominator. There are several conclusions that we can draw from these two formulas above. What we do, let's say these two formulas above. The important thing is, okay, the roots of numerator polynomial are called zeros. The roots of denominator polynomial are called poles. So if you compare zeros of GCS are from ns or kns, numerator polynomial is either ns or kns is equal to 0, and of gs was ns by ds are from ns is equal to 0, and poles of GCS are calculated from K times Ns plus ds is equal to 0, and of Gs, that is open loop transfer function, are from ds is equal to 0, because Gs was Ns by ds. So when we have implemented this feedback, what has changed? Zeros have not changed, poles have changed. So we can make a straight observation. Proportional feedback, proportional feedback means Hs is equal to some constant K, does not change zeros of the system, but changes poles of the system. ds is equal to 0 in open loop, 2 kns plus ds is equal to 0 in closed loop. So poles will change depending on what is the value of k. If k is equal to 0, both are same. Otherwise, poles will change. Whereas the numerator polynomial of the closed loop transfer function as well as the open loop transfer function are same. So zeros are not going to change. The poles are going to change. There are certain other things which may not be much relevant to you. If you compare these two transfer functions here and here, this one and this one, if you compare, you see that if k is equal to 0, suppose k is equal to 0, then the second case, that is the gain in the forward path, output becomes 0. So with 0 gain, output becomes 0. Whereas in the first case, if you have 0 gain, then closed loop transfer function becomes same as that of the open loop transfer function. There is no feedback, so closed loop becomes same as open loop. Whereas in the second case, k is equal to 0, output becomes 0. Likewise, if k is infinity, you have infinite gain, then the first case, the output will become 0. Ns by k, ns plus ds. So all those other terms will be negligible with respect to k. Final value will be 1 by k, output will become 0. K becomes infinity, infinitely large. Whereas in the second case, that is the controller is kept in the forward path, all other terms will disappear, will be negligible when k tends to infinity, the output will become 1. Okay? So there are differences. In the second case, with 0 gain, input 0 gain, output is 0. With infinite gain, output is 1. So it's a scaled system between 0 to 1. It will be scaled between 0 to 1. And whereas in the first one, if k is equal to 0, the system is same as open loop system. When k tends to infinity, the output becomes 0. So these two systems have their respective properties, and we will choose the particular feedback system depending on suitability. But as far as stability is concerned, both of these will have same denominator. So their stability is determined by the roots of the denominator, whether they have positive real part or negative real part. Then the stability is for all these two systems is same. It is all the same. You can use any one of them to determine the stability. So hereafter we will take a very simple mechanical system and we will try to show whatever we have done so far. All right?
Sir,
Yes.
so can we have a short break, please?
Okay. Fine. 5 minutes break. Today now it is 308. Okay. 313, 315. Okay.
Stop the recording, sir. Hello? On the